Hello everyone, welcome to the 21st lecture for the NPTEL course on computer system optimization for machine learning. Today as usual we will go with a brief recap and then we will continue on hybrid parallelism. In the last lecture we first discussed about data parallelism, then model parallelism, and then we discussed about pipeline parallelism. We discussed that in model parallelism and pipeline parallelism we split layers across different workers. Here workers are nothing but GPUs, but then what if a layer itself is so large that a GPU can handle it? That is why we discussed about tensor parallelism. Now in tensor parallelism we need to split a tensor into n chunks along a specific dimension, and each device only holds one by n of the whole tensor while not affecting the correctness of the computation graph. Again, when we say device we mean the GPUs. Okay. Now of course, I mean if we segment the model into or segment a tensor into n chunks and then map each of the chunks into individual GPUs, that will require additional communication to make sure that the result is correct, right. So that is the tensor parallelism. Now again we discussed about multiple types of parallelism, right, data parallelism, model parallelism, pipeline parallelism, and then there is this tensor parallelism. Now we also discussed that each of the parallelism technique has its own advantage as well as disadvantages, correct. So that is why there exists hybrid parallelism technique which tries to capture or which tries to leverage the advantage of all the parallelism technique. Okay. So again, I mean it is just for a reminder what is the system challenge during the training. So if you remember, like what if the input data set is very large, then we are doing the data parallelism. What if the model is very large, then we are doing model parallelism, tensor parallelism, pipeline parallelism, etc., right. So again, as a reminder, we have this input. During training we will perform a forward propagation which will do some prediction. At the same time we have these golden labels, cats or dogs. Then we will compute the error, then based on the error we will perform the backward propagation. So that is the DNN training, or I mean in general any ML model training. That is how any ML model training happens, right. So again at the same time our the model sizes are increasing day by day. Like for example, from 27 to 2022 we have seen models from 65 million parameters with models with 65 million parameters to model with like 1 trillion parameters. So that is how these model sizes have been increasing from for the past like maybe 10 years. So it is only 2022, today is 2026. So after 2022 there are even the model size increased even more, right. Now we already discussed that what if the input data set is very large. It is easy, you can use data parallelism where we just need to partition the input data and replicate the model. So let us say we have two input batches, batch 1 and batch 2. We can put batch 1 into first GPU and we can put the second batch into the second GPU. We have to replicate the model, right, because each GPU will perform the training on different input but on the same model. So that is the technique we need to incorporate if the input data set is very large. Now if the model is very large, it is difficult because we need to break the model itself. Like if we have a model of size 350 GB and let us say if we have two GPUs of only like 32 GB of capacity, then it is difficult to break the model also, right. The model itself does not fit onto the available resources. Not only that, we need to decide like how to break the model, how to split the model, how to partition a computational graph, right. We will see that there are lots and lots of ways to partition, and then you have to choose the right amount of partition or right partition, so that the overall execution time or the overall energy efficiency, etc., remains good, correct. Now I mean again, why is this challenging for a general computational graph? Whenever we say computational graph, that means we are saying we are taking one DNN model and then we are treating each of the layers or each of the maybe kernel or each of the computational element as one node. If that is the case, then each nodes are connected. So that is, I mean, if I mean, if you assume that one layer is one node, then there is a specific computation pattern from one layer to another, right. So, that creates a graph, correct. Now, for a general computational graph, we need to decide on which axis to break the model. I mean, we can do operator parallelism, we can do pipeline parallelism. Then how to efficiently map the GPUs to the resulting execution graph. Like, okay, I mean, we can we broke the graph or we split the graph, but then how to efficiently map the GPUs to the, I mean, how to efficiently use different GPUs to execute all those different components of the graph or different partition of the graph, right. Now, for general nonlinear graph, this leads to a combinatorically large search space. Like, for example, I mean, we will soon see one example like how big this search space can be, but then the motivation is to do an auto-parallelization, right. I mean, we should not say that, okay, if our DNN is like this and then if we have this much or this many resources, this much resource, then we should do this kind of parallelism. That there should be a technique which will take the DNN or which will take a ML model as input, as well as it should also take the available resource as the input, and then it will automatically say that, okay, this is the best parallelization strategy, right. So, there exist many parallelization strategies for different models. Like, we already talked about this data parallelism, operator parallelism, pipeline parallelism. Zero is another technique. It is a paper you can look up in the Google Scholar. It is another technique which introduces some parallelism. Then this axis is showing different ML model like CNNs, BERT, GPT, mixture of experts, all these models. And then there are different technique which is particular to one model, and then which is adhering one particular parallelism technique. Like, for an example, we have already discussed about GPipe, which introduces pipeline parallelism for BERT like models. Then there are other technique, and then you can see some icons. Those icons are nothing but PyTorch. I mean, there are Megatron. There are many like widely used tools or widely used libraries which incorporate a specific parallelism technique for specific DNN or specific ML model, right. But then we do not want that much specific, we want something more general. So, that is why we need something called auto-parallelization. But then, I mean, again, this is saying that ML developers needs to know which one is for their model and for their cluster, right. The people, the developers just like you, they should not worry about the device, they should not worry about the ML model. They are making the ML model, yes, but then they should not worry about which device they should run on, and etc., etc. So, that is why there has to be some technique which will automatically take the ML model as well as the available resource as input, and then parallelize the training, which will result in the best performance, right. But the problem, if we talk about the general problem, we need to maximize the performance given the model and the cluster. Again, cluster is nothing but the GPU cluster. So, we need to maximize, or we need to select the strategy which maximizes the performance across the model, I mean, maximize the performance across the given model as well as the cluster. And then this strategy can be a combination of interoperator and intra-operator parallelism. So, that is the auto-parallelization problem in general, like this is the mathematical problem of auto-parallelization. Now, let us visualize this kind of auto-parallelization. So, let us say we have this model. So, X is the input, and then we have matrix multiplication operation between weights and the input, and then it goes to ReLU, then another matrix multiplication between the activation and the weights, and then we get some output which is compared with the golden labels y, and then we compute the mean square error loss. That loss is getting propagated backwards to perform the training. That is the back propagation technique. So, this is the whole computational graph. When we talk about computational graph, we mean something like this. Now, this is just like, this is just a 2-layer perceptron or 2-layer neural network, right. You can imagine if we have like 100 layers, like DenseNet has 100 layers, right. So, this computational graph will be huge, correct. So, this is the DNN, this is the computational graph of the DNN or any ML model in general. Now, we have a cluster. So, when we say cluster, that means the cluster has multiple nodes, each node has multiple GPUs. So, in this particular case, there are 4 nodes in this cluster and each node contains 4 GPUs, correct. Now, whenever we say parallelizing the training, we can break the model into multiple axes, right. So, let us say A, B, C, D are 4 different nodes of the graph or 4 different nodes of the computational graph. Then we can either break this A, B horizontally, vertically, etc. Now, if you say this bounding box, that means we are mapping that particular part of the computational graph into one node, right. So, and again you can see different colors, that also means different GPUs. If we see a vertical line, that means we are partitioning the model in vertical direction or into one axis. If we see horizontal line, then that means we are partitioning the model into another axis, right. So, you can see that with just these 4 nodes and with just 4 GPU nodes and with just 4 nodes in the computational graph itself, A, B, C, D are the 4 nodes in the computational graph itself, there are so many parallelism strategy, right. So, that and then out of all these parallelism strategy, we have to select which is the best strategy, right. Now, just to give you an idea, like the search space is very huge. It is a huge search space for a real model. I mean, the nodes to color, I just showed you in the previous slide that there are 4 nodes in that example. There can be 100 to 10,000 operators in a real model, okay. And then the types of nodes or the types of operator can also be very huge, like it can be 80 to 200 plus. When we say types of operator, we can think that we have a 3 by 3 convolution versus 5 by 5 convolution, those two are 2 different types of operators, okay. So, there can be 80 to 200 plus operator type for a ML model, and the number of devices on a cluster, like the available colors again is like 10 to 1000. Like in a smaller cluster we can have just 10 GPUs, in a bigger cluster we can have 1000 GPUs. So, if you think like the worst case, in the worst case we have 10k nodes, 200 plus operator types and the thousands of devices in the cluster. So, in total the search space is huge, like we have to, if we want to come up with a best strategy which will do the best parallelization on the GPUs, that means we need to see which of these 10,000 operators and which of these 200 plus operators need to be mapped onto which of these thousands of GPUs. That is a huge search space, right. Now, to tackle this problem, I mean again that is the automatic parallelization method. There are many automatic parallelization methods in literature. So, this we can categorize all these automatic parallelization methods into 3 major category. One is search based method, another is learning based method and another is optimization based method. As you can see that there are many papers in the literature which falls into these category, okay. So, of course, we will not discuss all these papers, but I will strongly encourage you to go over most of these papers. They are all interesting papers, and since you know the context, you will also understand the most of the paper, okay. So, what I will do is I will sample one paper from each of these technique or from each of these category and I will try to explain, okay. So, in search based method, first we will start with this search based method which was proposed by Jia et al. In 2019. So, in this paper the authors first defined the search space. So, they named the search space as SOAP, samples, operators, attributes and parameters. So, that is the SOAP search space. Now, sample is nothing but the partitioning training samples. If we have large number of training samples, then we can partition the training sample into different segments or different buckets, and then we can have different GPUs to operate on those training samples. So, that is the data parallelism, right, that we have discussed already. And then we have operators, that is nothing but partitioning the DNN operator. So, let us say we can think that we have again let us say 3 GPUs. We can have like convolution 1, convolution 2 and convolution 3, that can be 3 different layers. So, 3 different layers can go onto 3 different GPUs. Okay. So, that is kind of model parallelism or pipeline parallelism, which we already discussed. Then attributes, we can further partition the attributes in a sample. So, for an example, let us say this is one plane or one particular operator. We can again partition the attribute in a sample, example different pixels, right. So, you can think that we have different planes of different dimension of activation. Now, each of the activation or each plane of the activation or each dimension of the activation goes on to different GPU. So, that is like different pixels. We can also parallelize across that attribute or that axis. And then parameters, we can also partition the parameters in an operator, like you can do parallelization for 1D convolution. So, for an example, you can think that I mean even if you take one dimension of input activation, you can further partition that input activation into multiple partition, and then each of the partition can be mapped onto one GPU. So, again remember, each of the partition will get convolved onto so many filters and so many kernels, right. So, we can say that each filter is getting executed, or each filter is getting executed on each of the partition, and each partition of the activation is mapped onto one GPU. So, these are the this is the search space, the whole search space. Now, on a very high level, when we talk about this SOAP search space, we have first is sample. We can partition in the sample dimension, which is nothing but the data parallelism. Another is operator placement, another is split, we can split the parameter, and finally the attribute is the rest of the things. Like if we can partition any other dimension apart from all these 3 dimensions, then the final one will be attribute. So, let us see how all these dimensions or how all these modalities in the search space are applicable onto different operators. So, let us say we have 1D pooling, then we can of course do parallelize, we can of course parallelize in terms of sample, we can also parallelize in terms of length and channel. Since there is no parameter for pooling, we do not need to, or we cannot partition, we cannot parallelize in terms of parameters, right. Now, for 1D and 2D convolution, again we can perform model parallelism. So, we can perform the parallelism in terms of sample. In terms of attribute, we can perform the parallelism in terms of length for 1D convolution and in terms of both height and width for 2D convolution. Now, since both 1D and 2D convolution has parameters, which is nothing but the weights. So, we can also do the parallelization in terms of channel, right. Now, if we have just matrix multiplication, then there is no convolution involved. So, 2 matrix will just get multiplied. So, we can just parallelize in terms of sample as well as channel. So, these are the different parallelism technique for different operator in terms of different modalities in the search space, right. So, again this particular figures are showing like how to do this parallelism, how to cut the whole cube, like one axis is channel, another axis is sample, another axis is length. Depending on how I cut the cube, different parallelism techniques are defined. Okay. So, that is the whole search space. Now, this particular technique Flexflow actually proposes a systematic way to devise a technique which will automatically search the best parallelism technique. So, let us see how it is done. Now, the input to the flow or input to the technique is DNN architecture as well as device topology. Now, whenever we say DNN architecture, we can think that it can be any ML model in general. Okay. So, in this case we can see that we have one matrix multiplication and then some, okay, sorry, it comes from the bottom. So, let us say we have 2 convolution operation, then some concatenation operation, and after that we have this matrix multiplication. So, let us say that is the like very naive, or that is some representative DNN architecture. And then in device topology, let us assume that we have two nodes, each node has one host CPU and then two GPU. So, you can see that both node has one host CPU and then two GPU. Both of the nodes are connected with the network. It can be like NVLink or some LAN or something like that. So, that is the device topology. Now, with this inputs, like again one input is the ML model architecture, another input is the device topology. Now, we have to know, or we have to discover what is the best parallelism strategy given these inputs, right. Now, in this Flexflow there is an execution optimizer. So, first it will select one candidate strategy. Now, candidate strategy, to begin with, it can be anything, like it can be any random strategy. Now, there is a execution simulator integrated on this technique. Now, the simulator says, like if we train the DNN architecture with that particular strategy, the performance will be something like this. Now, this is a simulator. Okay. Now, when we say simulator, it is not actually executing that DNN architecture, or it is that DNN architecture with that parallelism strategy, but it is trying to simulate, it is trying to guess the performance if that DNN architecture is parallelized using this particular candidate strategy. Okay. Now, of course, as you can imagine, that simulator has to be very fast, right, because I mean if it is not fast, if it takes like same time as the exact training, then there is no use of this simulator, correct. Now, once the simulator performs or evaluates the performance of the candidate strategy, then the simulated performance is fed to this Monte Carlo Markov chain search algorithm. So, MCMC search algorithm is nothing but Monte Carlo Markov chain, which is a very widely used popular technique for a guided search. Okay. Now, when we say guided search, we can think that let us say different configurations are getting fed onto this Monte Carlo Markov search algorithm along with the performance of those configuration, then it will guide the search. The Monte Carlo Markov chain, the MCMC algorithm will say like what should be the better strategy. Now, again that better strategy will be fed to the execution simulator. The simulator will say will provide the estimated performance of that particular search strategy, and this thing will go on, right. So, this search will be happening until it exhausts the time. That might be one time limit for the whole search space, for the whole flow. So, if the time is exhausted, then the search will be stopped, or I mean it can be the it is a possibility that there is no further improvement for the strategy, like it cannot improve the strategy for half of the search time. So, let us say we already spend n hours in the search, and then if we see that in another n hour there is no improve in the strategy, there is no improve in the performance, then that means most likely whatever strategy we have received so far is the best, or is the best possible strategy, right. So, that is the time limit, or that is the limit of the search, and of course, here the cost is to minimize the execution time. So, to minimize the execution time of the DNN training. So, this is the cost model. So, overall this is the cost model, execution simulator, and this is a search algorithm. So, as you can see, this specific technology, this Flexflow takes the ML model and then takes the device topology. After that, there is a execution simulator integrated with this Flexflow, which estimates the performance of training of that particular DNN architecture using one particular strategy. Then this Monte Carlo Markov chain search algorithm guides this strategy, or guides us to have a better strategy, and then again that better strategy will be fed to the execution simulator. So, this is an iterative technique. The search will be happening till the time limit is reached, or we can see that there is no further improvement in the performance of the strategy. Okay. So, that is the flex flow for you, and then once we obtain the strategy, then that strategy is deployed at the runtime. Okay. Now, let us quickly see the improvement with this particular technique. Now, the improvement, whenever we say improvement, so usually the improvement is shown in terms of throughput, like how many number of samples per second per GPU is performed or is obtained through one particular strategy, right. So, that is the definition of throughput. Now, as you can see in this figure, the authors have shown three different strategy. One is data parallelism, one is expert design strategy, like as a human, if one human being, if one expert has done many DNN training in their life, maybe there will be some intuition, right. So, with that intuition, that expert can design one good strategy, right. And finally, the flex flow is another strategy. So, they have shown the experiments, or they have performed the experiments in two GPUs, one is P100, another is K80. So, as you can see, for all the experiments, for all the GPUs, the flex flow has obtained the highest throughput always, right. If you see, let us take one particular example, let us say resonate with batch size of 64, you can see that this blue is always the highest. Probably this is not a good example. Let us take this NMT. Okay. NMT is one I think transformer model. So, if we see this NMT with batch size of 64, you will see that flex flow has always the best or the highest throughput. The x axis is showing the number of GPUs. If you see the number in the bracket is actually showing the number of nodes, and this number is the number of GPUs. So, 64 in bracket 116 means there are 16 nodes, each node has 4 GPUs. So, in total there are total 64 GPUs. Okay. So, as you can see that flex flow has always higher throughput than data parallelism or the expert design strategy. Now, another important thing to note is you can see that as we increase the number of GPU, these numbers are going down, right. Now, remember these numbers are number of samples per second per GPU, right. So, that means we do not have perfect scaling. So, we may assume that if we have 16 GPUs, our throughput will be 16 times. In that case, we should have all the lines should have followed one straight line like this, right. So, since we do not have perfect scaling, that is why the number of samples per second or throughput per GPU is actually reducing, right. Now, even if it is reducing, you may ask what is the benefit? The benefit is the number of samples per second is actually increasing. If you multiply this number by 16, that is definitely greater than this one, right. So, this is probably around this 250 mark, 250 multiplied by 16 is 4000, which is definitely more than 350. So, of course, I mean with more number of GPUs, we are having better throughput, per GPU is reducing. Again, why? Because there are communication time between GPUs and all those things. Okay. But going back at the point, what I wanted to say is with this automatic parallelism strategy, with that Monte Carlo Markov chain and etc., the overall throughput per GPU is increasing with respect to data parallelism as well as the expert driven or expert design strategy, both for K80 and P11, and that also is shown for multiple types of ML model, right. Now, with that, let us finish this lecture. In the next lecture, we will see more parallelism strategy and their results. Thank you very much.